All right, hey, brand new topic and very little math in this, so a lot of you will be glad about that. Some of you like the math in chemistry, but we're going to be teaching you Lewis dot structures today. So Lewis dot structure, named for Gilbert Lewis. He came up with a method of looking at the structure of compounds. And I'm sure you recognize all of these. Ethine, oxygen, remember just one carbon, methane, of course water, and carbon dioxide. So one thing we want to show you is how we know these are the correct structures. All right, so we're going to first start drawing. We're first going to look at Lewis dot structures of just atoms, okay, elements. So let's start with boron. So boron, capital B. Boron's right here. So hope you can see this little periodic table. Boron's right here. Now I have another periodic table over here if I need to look at it, but boron's right here. So what we do with a Lewis dot structure is just use dots to represent the valence electrons. So just remember what valence electrons are. Boron is 1s2, 2s2, 2p1. So valence electrons in the outermost energy level. So there's three here. 1, 2, 3. So the way we want to represent boron is just simply put 1, 2, 3 dots around the symbol. That's all. Notice I separated them as much as possible. We're not going to always have to draw the electron configuration. There's a shortcut to figuring out how many valence electrons atoms have. So looking at this periodic table, all these have 1, all these have 2. We skip the transition metals. We're only going to be bonding non-metals. 3, 4, 5, 6, 7, and 8. Of course, helium just has 2 electrons. So just a couple examples here. So chlorine, this is right here, would have 7 valence electrons. Let's see, phosphorus is right here, 5 valence electrons. Okay, so just look at a periodic table, count from left to right, 1, 2, 3, 4, 5, 6, 7, 8, and that's the number of valence electrons. Okay, let's look at carbon. Carbon is right next to boron, right there. Carbon has 6 total electrons, but 2 are in the first energy level. And we know that based on where it is, what family or group it's in, we know it has four valence electrons. 1, 2, 3, 4. Notice we just spread them out as much as possible here. Okay, looking at nitrogen. Nitrogen has 5 valence electrons. Nitrogen's right here, right there. Sorry about my shadow. So look at what we do now. 1, 2, 3, 4, 5. It's kind of like, remember the bus rule? We don't double up until we have to. So here we have to double up. This is called a lone pair. And these dots, of course, they represent electrons. This is where things are going to bond, okay? All right. So now let's look at, oh, excuse my reach. Let's look at a compound of boron. Let's look at boron trihydride, okay? So boron has 3 valence electrons. Hydrogen, how many electrons does valence electrons does hydrogen have? It just has 1 electron. And then what we do is we lasso those electrons up. That's what we do initially. And that is a bond. That's a covalent bond. We can have a bond here, and we have a bond here. If we draw this a different way, we can just simply draw dashes. A dash is 2 electrons, okay? So that's boron trihydride. How about let's look at a compound that contains carbon. Methane would be a good one. Carbon has 4 valence electrons, 1, 2, 3, 4. And then so we attach a hydrogen here, attach a hydrogen here, attach a hydrogen here, attach a hydrogen here. And doesn't that look just like that? So methane. All right. How about a compound of nitrogen? How about NF3, nitrogen trifluoride? Nitrogen trifluoride, non-ionic covalent compound. Okay, so let's start with nitrogen. We know that's the central atom. Nitrogen has 1, 2, 3, 4, 5. Hey, it wouldn't matter where you put that lone pair. Wouldn't matter. Now fluorine. Fluorine has, look here, fluorine's a halogen. Right there in the last group. That group there. It's not the last group, excuse me. They have 7 valence electrons. So fluorine's going to have 1, 2, 3, 4, 5, 6, 7. And we want to put that lone, that electron that's by itself with this electron so they can bond. And then we'd have a structure that looks like that. That's nitrogen trifluoride. Eventually, soon we'll learn that that's called pyramidal. The shape of that's pyramidal. This is tetrahedral, trigonal planar, but we're not ready for that yet. Let's try one more right here. Trying to think. Oh, let's look at oxygen, O2. Okay, so oxygen has 6 valence electrons. Oxygen is right here. 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So notice I conveniently, put these guys together so we can see here these electrons are going to bond. There's the lasso there. It's a covalent bond. And then these guys don't want to be by themselves. So there's a covalent bond there. Lewis dot structures. Hey, before I erase this, let me show you one thing here. Let's look at how many electrons are around this carbon in this compound. So look, how many are there? 1, 2, 3, 4, 5, 6. There's 8. How about around fluorine? There's 8. How about around nitrogen? There's 8. Around this oxygen, if you have to count all of these, that's 8. This oxygen has, count all those, that has 8. So there's something about having 8 electrons in the compound. Yeah, that's called, maybe you've heard of this before, it's called the octet rule. So most compounds follow the octet rule. Hydrogen, hydrogen, it only has 1 energy level. It just needs 2 electrons to fill that energy level. So I kind of think of this as the duet rule, but it follows the octet rule as well, duet rule. So hydrogen just needs 2. So if you look at all these hydrogen, there's 2 electrons around each of those. That's good to go. Now there are exceptions to the octet rule. For example, this first one we drew here, this guy, boron, only has 6. So there are some compounds that can be under the octet, some can be over the octet. I think we'll talk about those in a video later. Hey, let's get a little more sophisticated here. If you don't mind, I'm going to erase some of these and let's look at a couple others, okay? Give me one more second here. All right. I finally found a solvent that is good at erasing this dry erase, these dry erase markers. I was using Windex for a while. It didn't seem to work that well. I'm not sure what's in this. Anyhow, hey, let's look at something like this. H2CO. Okay, I'm going to teach you a different way now. So this is called the tally method. So what we first want to do is add up the valence electrons that are in this compound. So hydrogen, there's 2 of them, and each have 1 valence electron. Carbon, remember, has 4. Oxygen has 6. So we have 12 valence electrons to work with. Okay, this is called the tally method. You can always use the tally method. It always works. Okay, next step is draw the skeleton. So we know which atom is going to be the center. Hydrogen can't be in the center. Carbon, right? Carbon's in the center. So we're going to put carbon in the center. And what we're going to do is draw the skeleton. So this is just what's called the skeleton. Now, do you remember each dash, how many electrons does that represent? 2, right? So we just to draw the skeleton, we've used 1, 2, 3, 6 electrons. I'm going to subtract that from the total number. So we're left with 6 electrons, or divide by 2, 3 pairs. So we have 3 pairs left to make sure that octet rule is satisfied, okay? So let's just distribute these 3 pairs and see what happens. So we got 1, 2, all right. So let's make sure we have 12 valence electrons in this compound. 1, 2, 3, 4, 5, 6. 12, yeah, we have 12 electrons. So we gotta make, now, does this follow the octet? Hydrogen's cool. How about carbon? 1, 2, 3, 4, 5, 6, 7, 8. It's good. How about oxygen? 1, 2, 3, 4, 5, 6. Not good. 6. So watch what we do here. What we're gonna do is, so that this can follow the octet and carbon still follows the octet, we're gonna slide these two electrons in between. We do the old slide, and that forms a double bond. Now, if you look at, so let me do that again. We had this, excuse me, we had this. We noticed there was only 6 electrons on oxygen. Oxygen always follows the octet. Carbon does too. So what we want to do is use these 2 electrons for both the oxygen and the carbon. The way we do that is we can put them in between. Now, does that follow the octet? Let's see. 8, 8, 2, 2. We're good to go. Check, follows the octet. All right, maybe we should try one more of those, okay? Let's look at C2H4, ethene, right? Ethene. Let's count up the valence electrons. So it says 8 plus 4 is 12 again. We have 12. Does that make sense what we did there? So we have 1, 2, 3, 4, 5. So we already used 10 electrons. We're only left with 2 electrons. Of course, that's got to be a double bond. Well, you know that because ethene has a double bond. So that maybe is not a good example. I have a feeling this video has been long enough, so let's just review. Lewis dot structures. We let dots represent the valence electrons. We place them around the symbol of the element like this. We don't double up until we have to. How do we know how many valence electrons? Look at the periodic table. Just count from left to right. Let's see. Sulfur's right here. We would have 6 valence electrons. So I'll give you a bunch of these to do. Good luck with that. This is going to be really important. This won't go away. We'll start looking at balloon models. We'll start looking at shapes of molecules. Then we'll start looking at whether a molecule is polar or non-polar and how they attract each other. So there's a lot. This is the basis for a lot of things we're going to do the next, say, 2 weeks, a week and a half or so. Okay? All right, bye. That was way too long. That was